All right, this video lesson is on modeling, and we're going to do some modeling of applied max and min problems. Now, these are problems that we're going to be able to solve in calculus using derivatives, but it's nice to know that we can also solve these in pre-calculus using our calculator and finding maxes and mins. So let's do some modeling. The first problem I've got for us to solve is find the dimensions of a rectangle with a perimeter of 100 feet whose area is as large as possible. So the first thing we need to do is figure out what are we trying to find the max or the min of. Well, in this case, we're trying to find the area that's as large as possible. So I know that I'm going to have an area function that I find the maximum of. And then, so I need to know what the situation looks like. And I'm going to draw a rectangle because the best thing to do is to draw a picture. So here's my rectangle. It doesn't have to be perfect. And I don't know the dimensions of the rectangle, so I'm going to call this one X and this one Y. And of course, you could call them L and W, depending upon what your preference is, but I like X and Y. And I have a physical constraint in this problem. The constraint is that the perimeter has to equal 100 feet. So the expression for the perimeter is going to be 2X plus 2Y equals 100. And I could reduce this equation by dividing everything by 2 and state that X plus Y has to equal 50. So this is a constraint on my area. So what is the area of this rectangle? Well, the area of this rectangle is going to be X times Y. But I can't type in X times Y in my calculator. I have a Y equals button. So I have to have this area as a function of one variable so that I can put it in my calculator. And the good news is that I have a piece of information here that I can use to solve for one of the other variables. So we're going to solve for this equation for Y. And when we do that, we get Y equals 50 minus X. And so that's 50 minus X. I can plug that in here. I can substitute. Into this equation and say, all right, well, the area as a function of X is equal to X times 50 minus X. All right, well, let's simplify that a little bit by multiplying it out. And we're going to multiply this out. Ordinarily, you wouldn't have to, except that I know that this is going to turn out to be a quadratic. And this quadratic is upside down, so I know it's going to have a maximum. And we're going to do this without a calculator and with the calculator since it's a quadratic, because we have a nice method to find the vertex here. But let's think about really quickly what the domain is on this problem. First of all, I know that X has to be bigger than 0 or else I don't have a rectangle. So I know that the 0 is going to be my end here. And now the dimensions are X and Y. And so here are my dimensions, X, Y, and these are my dimensions algebraically here, X and Y. And I know that X has to be greater than 0, but this dimension here implies that X has to be less than 50, because if X is bigger than 50, this Y or this width here is going to be a negative number, and I can't have that. So my domain is going to be from 0 to 50. All right. Now, I know that this is an upside down parabola because the coefficient here, this A value here is negative. Without a calculator, we can solve this problem to find the vertex and thus the maximum area. And how do we do that? Let's see. Well, oh yeah, I heard an answer there way from the back. It was very faint, but I heard completing the square. Yes, so you're going to have to complete the square. All right, so how do we complete the square? Well, first thing I'm going to do is finding the vertex by completing the square. And I know everyone was cheering when I said that. Ha ha ha, right? Okay, so I'm going to rewrite my equation as a equals negative x squared plus 50x. Now, in order to complete the square, I have to have a positive 1 in front of my x squared term, which I don't have. So I'm going to factor out a negative here, and then I get x squared, and I have to flip this sign, minus 50x plus something. All right, well, when I add that plus something, how do I figure out what that is? Well, when you're completing the square, you have to take half of the middle term, which is negative 50 over 2, and then you have to square it. All right, so that would be equal to negative x squared minus 50x. And then if we take half of negative 50 here, we get 25. And when we square that, we get 625. All right, but now I've made this side of the equation heavier, but not really heavier. But I'm subtracting from this side of the equation a negative 625. So I have to do the same thing from this side so that I maintain the equality. All right, when I do that, I get a minus 625 is equal to negative, and now this is a perfect square and it's very happy. So this is going to be x minus, you could factor this, but you'll find that it's going to be x minus 25 quantity squared. And now I've got to get the area function all by itself. So I get negative x minus 25 quantity squared plus 625. And I know the vertex is going to be, in this case, 25, 625. Now, before we go on, what does this mean physically here? This means that the x here is x, and the 625 is a of x, which means this is the dimension. This is the dimension, and the a of x is the max area. Okay, but the question didn't ask us that. The question asked us, find the dimensions of the rectangle. Find the dimensions of the rectangle. So I have the x is 25, and I have the maximum area, but I don't have the maximum area and the y direction, the y dimension. So I need to solve for y. So if x equals 25 and y equals 50 minus x, then y has to also equal 25. And so this is how I would answer this question. I would say the maximum area of 625, and my units are feet, so I'm going to say feet squared, occurs when dimensions of rectangle are 25 feet by 25 feet. All right. Now we did that by completing the square, and we didn't even use a calculator, which is pretty cool. But we're going to verify it on our calculator. So here's my handy dandy calculator. Turning it on. Okay, so we're going to go to y equals here, clear out my function here, and then I'm going to plug in the area function. It doesn't matter if I plug in the factored form or the standard form here. So I'm just going to type in x times 50 minus x, because that was the first equation I found. All right, now I know that the maximum happens to be 625. So if the maximum is 625, it's in the y direction. I know I'm probably going to have to change my window. So I'm going to go to my window here and change my maximum to 625, but I'm going to make it bigger than that. I'm going to make it 750, just so we have some clearance in the top here. And then I know that my maximum x is going to be 25. So let's give that some clearance too, and let's just make that 75. All right, and now I'm going to hit the graph button. And there is my parabola that I expected, and it is indeed upside down. And now I'm going to try to find the maximum. So how do we do that? Well, we go second, calculate the maximum, which is number 4. And what's really cool about these 84 calculators and the 89 is that it's asking you, what is the left bound that you want here? And since we know that this is 25, what I'm going to do is I'm going to type in a left bound of 20. Yes, you can specify where you want the left bound to be, which is really cool. And I'm going to let the right bound be 30. Now, if you didn't want to specify that, you could arrow over and all of that, but this I find is to be pretty quick, especially if you know kind of where it is. All right, and then do you want the calculator to guess? Yes, I would. And there it is. The calculator says the maximum occurs when x is 25 and the maximum area is 625. So you know how to solve it by completing the square and by finding the maximum on the calculator. All right, so that's the first one. All right, well, not all of them we can solve by completing the square. Sometimes most of these we're going to have to use our calculator. But I just wanted to show you one where you could solve using completing the square as well. All right. This next problem is identical or close to your problem of the week that you had last week. And we're creating an open box from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal sides from the 4 corners. So let's draw a picture here. Here's my rectangle, and here are my corners that are all going to be the same. And since we don't know what size we want them to be, we're going to call them X. Okay, and we know that this is going to be 16 because it's the shorter side, and that's the way I drew it. And we know this will be 30. And what we're going to do is we're going to fold these corners up, and the box is going to then look like something like this. Sorry, I can't speak and draw at the same time, so you're stuck with that. All right, so if I was trying to find the volume of this box, because this is going to be the inside here, the volume of this box is going to be X by, this is the short side, and this is going to be 16 minus X, so it'll be 16 minus 2X. And this long side here is going to be 30 minus X, which is 30 minus 2X. And so the volume of our box is going to be X, which is length times width times height, which will be X times 16 minus 2X times 30 minus 2X. Okay, now what's our domain here? Well, I mean, clearly we know that X has to be bigger than 0 or we don't have a problem. So we're going to put 0 here. And now the other constraint is going to be the fact that we can't have a negative side. Well, we know X is positive because we already said it has to be bigger than 0. This side says, well, guess what, folks? I can have X equal anything 8 or smaller, less than 8. Because if X is 8, then I'm 0, and I can't be a 0 side. And if X is bigger than 8, then I'm negative. And this side says, well, that's okay with me. I'm allowed to have sides that are 15 or less. So which one is the bigger constraint? This one says I got to be bigger than 0. This one says I have to be bigger than 0 but less than 8. And this side says, well, I have to be bigger than 0 but less than 15. So this is the big constraint here. So we're going to say the domain is from 0 to 8 for this function. All right, now I don't recommend for the purposes of this problem, because we're just trying to find the maximum volume and what X will create that. I don't recommend us multiplying this out because this is a calculator question. And so what we're going to do is just that. Use our calculator to find the maximum here. So I'm going to turn it on again. And we're going to go to y equals here. And let's type in our volume function, which is x times 16 minus 2x times 30 minus 2x. All right, and there's our volume equation. And I think this is going to be a pretty decently large volume because, you know, we have 16 times 30 in here somewhere. So I'm just going to leave my window the same. I have it at 750. And I know that it has to be, let's go back to the window. So I'm going to leave this value at 750 because I'm thinking it's going to be pretty big. I might have to adjust it, but we'll see. The X max I know is going to have to be between, you know, 0 and 8, we hope. So I'm going to reduce this a little bit and say, I don't know, let's try 20 because I want to include this in here too. All right, so let's grab it and see if we got the maximum in there anywhere. Well, I was really lucky because it looks like the maximum is in here, which is nice. And my zeros here are 0, 8, and it looks like it is indeed 15. So let's use our calculator to calculate the maximum. So we're going to go second, calculate the maximum, number 4. And I'm going to tell the calculator I want the left bound to be 0. And I want the right bound to be 8 because I know that's my other 0 here. And then I'm going to press enter because I want the calculator to guess. And it's going to tell me that the max volume occurs when x is 3.333 repeating. So the maximum volume, let's write this down, and that's 725.93, and this is cubic inches, occurs when x equals 3.33 repeating, which is actually the same as 10/3 inches cubed, because that's 3 1/3. Not inches cubed, I'm sorry, that's just inches. All right, so this says what size should the squares be? And of course I can't spell squares, but I are an engineer. So we're going to say, so squares should be 10/3 inches by 10/3 inches to be creating a box of maximum volume. Okay, now, yesterday's group asked me, well, Mrs. Muller, can I just leave it as 3.33 repeating? And the answer is yes. This is an exact answer, 10/3. And this is, you know, with the bars, I guess it's exact, but this to me is cleaner. But yes, I would accept both is the answer to the question. All right, so anybody got any questions? Oh, wait, this is a video. So no, you can't have questions. All right. Let's move on to the next question. So that's maximizing the volume of a box by cutting out squares. All right, the next question I have is, let's find the radius and height of a right circular cylinder of largest volume that can be inscribed. Now, inscribed means inside a right circular cone with a radius of 6 and a height of 10 inches. So I'm sticking a cone inside a radius. I mean, a cone inside a, let's say that again. I'm sticking a cylinder inside a right circular cone. So let's draw a picture. And we don't have to be Rembrandt or whatever your favorite artist might be, like Monet or I don't even know artists really. Okay, so there's my right circular cone. And I'm going to put a right circular cylinder inside of it. Now, I have been drawing these things for years, so don't be hard on yourself if you're not perfect drawing these, and I'm certainly not either. Okay, so there it is. There's my not perfectly sized. So the radius here of the cone is 6, and the height of the cone here is 10. So I'm going to label that on the outside. So this height is 10. And the radius is 6. And okay, so the radius of this here is R, and the height of my cylinder is H. Okay, so what are we trying to find the maximum or the minimum of? Well, this problem says find the radius and height of the right cylinder of largest volume. So I need the volume of a cylinder. Well, I happen to know that the volume of a cylinder is pi r squared h, which is the area of the base times its height. Okay, and this is equal to the volume of a right circular cylinder. Okay, and like problem number 1, I'm trying to find the volume here. Well, the problem with finding the volume, pi r squared h, is that I've got too many variables over here, because in my y equals in the calculator, I can only put one variable, and that's x. And sadly, I have a varying r and a varying h here. And so I need to come up with something else that will help me eliminate one of those variables from this picture. So the good news is that I can use something that I learned in the past. And I know that you might not have seen it right away, but embedded in this beautiful little picture here, we can use similar triangles. Now, this right here is a big triangle, and I hope you can see that. And there's also a smaller triangle up here that is similar. So I am going to pull out that triangle here for us to analyze. So using similar triangles. I know that this is 6 because the problem stated that, and this is 10, which is this distance from here to here. And I know that this distance here to here in the inside here is h, and this is r. Now I could say something like 10 is to 6 as this distance is to r, but I don't know what this distance is right here. So I have to figure that out. So if this is 10 and this is h down here, what does this distance have to be? Oh, yeah, I heard it from the back. This distance here has to be 10 minus h. So using similar triangles, I can say 10 is to 6 as 10 minus h is to r. Now, there are many ways you can set up this ratio. You can set up this ratio saying r is to 6 as 10 minus h is to 10. You can say 6 is to r as 10 is to 10 minus h. But as long as you're consistent, it doesn't matter which way you set up the ratio because you'll get the same thing. Now, so now I have a relationship here between h and r that I can use to substitute into this equation here, pi r squared h. And there's an easy way to go, and there's a more difficult way to go. If I were to solve this equation for r and plug it in here, I'd have to square whatever it is when I plug it in. So I would like to avoid the squaring thing. And I think I want to solve this equation for h because I don't have to square whatever I put in for h. All right, so let's take this equation and cross multiply. And so we'll say this is 10r equals 6 times 10 minus h. And so let's simplify a bit. This is 6d minus 6h. And I'm going to solve this for h. So I'm going to move the 6h over here. And I'm going to say 60 minus 10r. Divide by 6. So I'm going to get 60 over 6, which is 10. And then minus 10 over 6r. But I can reduce that to 10 minus 5/3 r. So I'm going to take this expression here for h and substitute it into this equation. So we're going to get the volume equals, I can say volume of r, because it'll be a function of r only, is equal to pi times r squared times my expression for h, which is 10 minus 5/3 r. So this is the equation right here that I am going to plug in the calculator. You know, we could multiply that out if you want to, but we're just trying to find the maximum. And in order to find the maximum, I don't have to have it multiplied out. I can just type it in my calculator. All righty, so here comes the calculator. Oh, wait, before we do this, I heard a little comment from the back there. We really should figure out what the domain is here on R. In order for this problem to exist, R has to be bigger than 0. But what do you suppose, in order for this to work, it has to be? Do you suspect that R has to be less than 6? Because I think if we put 6 in here, in this expression for h, it's equal to 0, isn't it? So 10 minus 10 sixths times 6 is equal to 10 minus 10, which is 0. So I think R has to lie between 0 and 6, which is going to help us with our calculator and setting up the window. All right, so let's do this. Plug it in. So we're going to go y equals, let's clear this out, and type in our equation, which is going to be pi. So we're going to go second pi, parentheses, times x to the second, parentheses, times 10 minus 5 divided by 3, x. Now I had a discussion yesterday about, well, Mrs. Muller, don't you have to put something in parentheses here with this 5/3 or something in parentheses? Well, the good news is the calculus is going to work this problem using PEMDAS, and PEMDAS says parentheses, exponents, multiplication, and then division. So this calculator is going to go 5 divided by 3 times x. Now, if this denominator was in parentheses, then it would be 5 over the entire 3x. But yeah, you don't need parentheses here. Okay, so that looks good. So I'm just going to look at the graph and see if I should adjust the window. Let's see. I've got my window to 20 in the x, and I don't know about the max. So let's see what the graph looks like and see if I can even see it. All right. I would say that's high enough, don't you think? I mean, I've got a lot of space here, but I mean, I can see the maximum pretty clearly. So I'm going to just use this window by default. Okay. So in order to find the maximum, we're going to have our calculator say second calculate the maximum, which is number 4. And I know my left bound is going to be 0. And I know the other 0 we discussed was 6. So I'm going to put 6. Would you like the calculator to guess? Yes, I would. And it says here, I don't know if you can see it, that that's 4. So R is going to equal 4.000009, which is essentially 4. And the point's going to be 4, 167.55. Okay, now let's discuss what this is. This is R, and this is the maximum volume. That's not H. So how do I figure out what H is? It's the maximum volume. So how do I figure out what H is? Well, do I have an expression for H? I sure do. H is right here. So if R is 4, H is going to equal 10 minus 5/3 R. So H equals 10 minus 5/3 times 4. All right, so H is going to equal, well, let's see, that's going to be 10 minus 20/3. which is going to be 30/3 minus 10/3. 20/3, sorry, which is 10/3. So if R is going to equal 4 and H is going to equal 10/3, I can write my solution to the problem, which says, find the radius and the height. So I can say maximum volume of 167.55, and this is in inches as well, cubic inches, occurs, I can't spell occurs when R equals 4 inches and H equals 10/3 inches. And so then there's our answer. All right, so sometimes you have to be creative and figure out another relationship between your two variables here in order to solve the problem. And similar triangles is a very common technique to use. So that's why I like to do this example. All right, moving right along. Here's another cool real life situation. And this is a closed cylindrical can is to hold 1 liter or 1,000 cubic centimeters of liquid, which is a volume. How should we choose the height and radius to minimize the amount of material needed to manufacture the can? So we're going to minimize something now instead of maximize it. So what are they telling us here? They're saying a closed cylindrical can. So here's my closed cylindrical can. Okay, there it is. It has a volume of 1,000 cubic centimeters. Now, volume of a closed cylindrical can is equal to, as we just stated in the other problem, whoops, it really should be in the middle here, and that's H. All right, is equal to pi r squared H, which is the area of the top times its height. All right, but what are we minimizing? We're minimizing the amount of material needed to manufacture the can. The amount of material, that sounds to me like a surface area that we want to find an equation for. So surface area of a right circular cylinder, and it says it's closed here. So if it's closed, that means I need a top and a bottom. So surface area, what is the area of the top and the bottom of this can? Well, the top is a circle, and the area of that is pi r squared. And the area of the bottom obviously will be pi r squared. So the first part of this surface area equation is going to be 2 pi r squared, because that's the top and the bottom, plus I need the area of the outside. Well, the area of the outside, well, it's kind of an awkward area, but since I have the ability to show you a picture, which is very, very cool, if I were to make a cylindrical can out of this piece of paper here, there it is. It's a, pretend that that's a circle. We're having fun. All right. And I were to, cut this circle down the seam here, it turns out to be a rectangle. Okay, so I need the dimensions of the rectangle, which are going to be this and this dimension and that dimension. All right, so what is that? Well, the top is nothing but a perimeter of a circle. Well, perimeter for a circle is a fancy way of saying circumference. So it will be the circumference times the height. So it's going to be 2 pi r times the height, because if we have it circular, 2 pi r is this distance, and the height would be this distance, okay? So the next dimension, or the next part of the surface area, is going to be 2 pi r h. Well, now we face the same similar situation we got here. And what do we have? We have too many variables on the right-hand side of this equation. So with too many variables, I better have some kind of relationship between h and r so that I can substitute in here. Well, lo and behold, right above here, I have 1,000 equals pi r squared h. So I can take this equation here and solve for one of the variables in order to substitute into this equation. Now, there's an easy way to do this and a more difficult way to do this. We could solve this for r. If we solve this for r, it's going to require square roots, which will be uncomfortable. Okay. And then we'd have to have a square root in this equation. We could do that if we wanted to, but I think that's harder. Or we could solve this for h and plug it in one time for h here and not have to square it or anything. So I think we're going to take this equation right here and solve it for h. So we can say then that h equals 1,000 over pi r squared. That's pretty simple. And we can take this expression now and substitute it in for h. All right, so let's do that. We get 2 pi r squared plus 2 pi r times our expression for h, which is 1,000 over pi r squared. And we can simplify. We can say 2 pi r squared plus 2 pi. Well, what happens here before I simplify that? Can you see that a pi cancels and one of the r's cancels, which is really, really nice. And so we can say that this is 2,000 divided by r. So that's the surface area equation. Now, I could find a common denominator and all that stuff, but I'm just trying to find a minimum. And if I'm trying to find a minimum using the calculator, I really don't have to do any more than just have the equation and stick it in my calculator. Now, the domain here on r has to be bigger than 0, but I'm going to leave this blank for now, and we'll have a discussion about that in a second. All right, so I'm pulling out the calculator, and you should do the same. And here it is. That's my old function, so I'm going to clear that out and hit y equals. And let's type it in to second pi. And now somebody in class yesterday asked, Mrs. Muller, can we factor out a 2 pi r? Well, you can, except you notice that this r cancels. So I mean, yes, you could, but I would just leave it like that and cancel these and make your equation simpler. All right, so this is 2 pi. I'm going to put x squared plus 2,000 divided by x. And then I know that r has to be bigger than 0. And I see that this is a big 2,000 here, so I'm going to have to change my window, I think. So let's change our window to, I'm going to put 2,000 just because if that's a 2,000. And I think it's certainly going to be less than 20. So let's just see the graph. Ah, there we go. So I can actually, now I promise you, the only reason I made the window in the y direction 2,000 is because this equation had a 2,000 in it, and I may or might have had to adjust this. If you put 1,000, I'm not sure it would work. Let's see what happens if I change it to 1,000, just because, you know, somebody might do that and they might wonder if that's okay. And look, 1,000 works too. So I'm just going to leave it 1,000. Let's say you didn't see a minimum anywhere on your screen. You just have to adjust the window somehow. And I would use my equation as my guide to figure out what I might put for the dimensions. Okay. All right. So I need to find a minimum. So I'm going to go second, calculate a minimum, which is number 3 now. And I'm just going to go left and right here on the left bound and the right bound to show you that we can do that. Just make sure I'm well enough over. And do I want the calculator to guess? I do indeed. And the point's going to be 5.419, comma 553.58. So let's discuss what these units are. These units are r, and this is the surface area as a function of r. So this is r, and then this is going to be the what here? Max surface area. Okay, and this question asked us for how should we choose the height and the radius? Well, we found the radius. Now, how do we find the height? Well, if we know the radius here is 5.419, I can use this r and plug it in here to solve for h. Okay, so I'm going to say h equals 1,000 over pi times 5.419 quantity squared. Now, I am a stickler for using exact values, and so I would like us to use the exact value that this calculator has, okay, which is 5.4192605. Now, how do I do that? Well, if you go back to the, let's quit out of here, quit here. What the calculator does when it finds a minimum or a maximum or something like that is it's going to store it in X. So I'm going to say X, and if you press X, what comes out here? Wow, look at that. That comes out. And if I were to hit, I think it's alpha F4, where we get Y1, Y2, and all that stuff. So if I pipe in Y1 of X, what pops out? The surface area, which is pretty cool, I think. But I'm going to store X so that I have it for all time. So I can hit X, stow, alpha A. Okay, there it is. And if I wanted to store the surface area, I could store it in, I could say, I'm going to copy this right here. Well, I don't really even have to do that because I could type in here A now, alpha A, and I would have it. You see how that is? I wouldn't store the Y value. I just store the X. All right, so what we're going to try to do is find H. So I'm going to use my calculator and go 1,000 divided by parentheses, second pi. Now, why did I use parentheses? Because this is all in the denominator, okay? And now I can go alpha A squared, enter. And that's going to be 10.839 centimeters cubed, or 10.84 centimeters. Oh, I'm sorry, it's not cubed. It's not a volume. Centimeters. Okay. Now, if you didn't find another minimum or a maximum in between the time that you were calculating, you could use this expression here, and you could still use an X. And you see it works. I just like to store my variables so that if I forgot that I went and found a minimum or a maximum somewhere, at least I know I stored it in A. And then if you had more than one problem, you could store the other answer in B, C, D, or whatever, okay? All right, but this one wants the radius and the height. So this is how I'd answer this question. I would say the maximum, or no, I want minimum, don't I? Sorry, minimum. And this is a minimum. My goodness gracious, got to fix that. The minimum material of, and that's 553.58, and it's going to be centimeters squared because that's an area, will be used when R equals 5.419 centimeters and H is 10.839 centimeters. Okay, now we did not talk about the finishing of the domain here on R, so let's do that really quickly. I'm going to go to the graph here, and does this look like R is going to be limited at all? This looks like if as R goes to infinity or X goes to infinity, R is rocketing off into space, where the function's rocketing off into space. So this, believe it or not, is infinity. Now, what kind of can are we going to have if R is very, very large? If R is very, very large and my volume is remaining the same, the H is going to be very, very small. So this is going to be a very small can if R goes to infinity. So almost flat. So that's not really realistic. It'd be a long, flat piece of paper. But technically, the radius could go to infinity. All right, which is kind of a cool thought there. All right. One last problem, and this is a classic kind of problem. And it's a nice, cool algebraic problem that says, find a point on the curve y equals x squared that is closest to the point 18, 0. Now, I'm such a visual person, I like to draw a picture. Let's do that. I'm drawing a picture. This is y equals x squared. A rough drawing of y equals x squared. And 18, 0, gosh, is going to be way the heck over here. And I want to find the point on the curve that's closest to 18, 0. Now, I suspect it's going to be on this branch of x squared because it's the closer branch. So I'm just going to put a point here, x, y, and some generic point. And I want to find out what point on this curve is going to be the closest. So what am I doing here? The closest. Sounds like I'm trying to find a minimum. A minimum what? Well, a minimum distance. And I'm going to refresh your memory. The distance formula is equal to, yes, I hear groans in the background, is equal to x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And I'm trying to find a minimum of this equation here. All right, now, so let's do that. So we'll say the distance is equal to the square root of, well, what's the distance between these 2 points? It's going to be x minus 18 quantity squared plus y minus 0 quantity squared. Okay, well, interestingly enough, I have an equation for distance. And how many variables do I have here? Well, gosh, I've got 2. And in my calculator, when I put in y equals, I only had the ability to put 1 variable. So I have to think of something. Well, guess what? This point, xy, could be rewritten as x comma something else. Well, what does y equal? Well, y happens to be x squared, so I could put x squared here. So I can say this point then is really x comma x squared. And I could rewrite this expression as d equals the square root of x minus 18 quantity squared plus x squared minus 0, which is just x squared, squared. And I could simplify that and say the square root of x minus 18 quantity squared plus x to the 4th. All right, well, so I have an expression. And I could call this function d of x now because d is a function, the distance is just a function of x, which is pretty cool. All right, so let's talk about the domain of x here. Well, the distance is going to have to be greater than 0, but less than, do you suspect it's going to be less than 18? I think it's going to be less than 18. But we'll put this temporarily and see what happens. So now we're going to take our calculator and see if we can find a distance, a minimum. So let's go y equals, clear this out, and we're going to go second square root of parentheses x minus 18 squared plus x to the 4th, and press enter. And I'm just going to leave the window alone to play with it in just a second. So let's see what the graph looks like. Wow, it looks like it might have some kind of minimum in here somewhere, but I need to zoom in. So I'm going to change my window to, it's looking like it's going to be a lot less than that. So let's just put 10. And I'm going to put my maximum, I think I'm going to put 20. I think it's going to be less than 18. So I'm just going to put 20 because you see this distance from 0 to here is going to be 18. And I'm guessing it'll be less than, just a little bit less than 18 maybe. I don't know. Well, maybe I do, but you know, that's kind of what I would guess if I was trying to graph it. So let's see what happens when I graph it. Oh, well, then I have a little blurb up here. That's a minimum. And if let's say we wanted to see more of it, I could change this to 30. Now 20 is perfectly fine. I just want to see more of it on my graph, okay? All right, and I want the minimum there, so let's see. To find the minimum, we're going to go second calculate the minimum, which is number 3. Oh, 0 is good enough left bound. And let's go to the other side and press enter. All right, and my minimum point is going to be 2, comma, and that's 16.492. So what does this point represent? This point represents an x and a d of x, right? So this is the minimum. The minimum distance. Okay? That's the minimum distance, and this is the x where it occurs. All right? So if that's the minimum distance, and I want the point that's closest on the curve, okay? And the point is x, comma, x squared. So I'm going to take x, and that's 2, and x squared is going to be 4. And so the point on the curve that'll be closest to 18, 0 is going to be 2, 4. So how would I write that? I would say the point 2, 4 on y equals x squared is closest, closest to 18, 0, and the distance is 16.492, and I'm going to put units here because they don't tell us what the units are. Okay, so that is it in a nutshell. That's all I wanted to do do some modeling. So the homework is in the book, and I will have an extra practice modeling on Moodle. It's totally optional. And I'm going to also put some practice transformation stuff on Moodle for those of you who might want to practice some before our quiz, which is not next time, but the time after. So we will chat with you next time. Thanks for listening.